All right, welcome to section 3.2 on differentiability. Differentiability just means like, is a function differentiable? So when is a function differentiable? Finding the derivative again means finding the slope. So if I'm asking if it's differentiable, I'm asking if I can find the derivative. Can I find the slope? And essentially there's two cases that are going to cause me a problem for that. And they're actually pretty easy, and we're going to go through them in detail in a minute. But the two cases are basically this. Either a function is not differentiable when the slopes from the left and the right of that point don't agree, or it's not differentiable when there's a discontinuity. Because if we think about that, for most continuous functions, I'm just going to make something up. Most continuous functions, we can find a slope. Like if I look at this point here, yeah, that's definitely increasing at that point. At this point here, it's decreasing. At this point there, slope's increasing. So most points of a function, we're going to be able to find a slope, which means it's differentiable. There are a few that cause me problems. And one of them is right there, right at that top there. Because if I say right at that point, you can't really say it's increasing or decreasing or zero, because it seems to be going up on the one side, but down on the other, and it didn't seem to flatten out, right? There's a difference between that and this, right? With this one here in yellow, it's clearly has a slope of 0 at that top. But this one on the bottom, I'll put that in red, that was just a sharp corner. It didn't like flatten out to a slope of 0. It just suddenly changed directions. There's not like the slope is going up on one side and down on the other. It's going to be hard to say what the slope is. In fact, I can't really say what the slope is. Same thing here, like I'm going here this direction, so I suddenly jump there. Discontinuities are a problem. Turns out when we explore these a little bit further, it's actually really easy to identify, especially when looking at a graph, whether a function is differentiable or not. So we're going to run through a few quick examples. This video should hopefully be on the shorter side and not too hard. All right, so first one is a case like this. In fact, we were just talking about this one, where you're traveling along and then all of a sudden you switch directions, right? Something like that is a problem because the derivative, when we talk here, right-hand derivative, we could work out the math, or we could just look at it like, hey, I know this derivative on the right-hand side, that's just going up and up and up. It's this equation here, f of x equals x. I know the line y equals x has a slope of 1. So from the right, it has a slope of 1. But on the left-hand side, it has a slope of -1. And it just switches. We're going to slope of -1, -1, and then we're going up. That switch is a problem because I can't say what the slope is exactly at that corner, at that problem. So this one is not differentiable at that point right there. That kind of point's given a name. It's called a corner. So one thing is functions are not differentiable at corners. So if you've got some function to go along here and all of a sudden you see that sharp corner, not differentiable. Just make sure you understand the difference between a corner, and a not corner, right? That's a corner. It's not differentiable. It comes to a sharp point, a sharp peak. This is not a corner. That's just a curve. Even if I make a sharp curve, like whoosh, still a curve. There's a difference between a sharp curve and a corner. So corners are a problem. Can't differentiate at corners. All right. This is a similar type of one. It's just given a different name. You'll notice for this particular function, y equals x to the 2/3, the function's going down, 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 down. You can't quite see it here because it's not a great graph, but if you graph this function, it really does something like this. Where from this side, the slope keeps getting more and more negative. It's kind of dropping off down towards a slope of -infinity. On the other side, it's shooting way up with the slope of infinity, right? So that line right there is a problem. Like it's kind of like going like this. It's given a name. It's kind of like a corner, but instead of being a corner where a corner goes to a sharp edge, this one actually shoots down towards infinity and then back up. I can't have a slope of infinity. It doesn't agree from the left and the right. That's a problem. This thing is called a cusp. So cusps. Functions are not differentiable at cusps. There's going to be 4 cases where functions are not differentiables. We already covered 2 of them. One is corners, one is cusps. The next one is probably the hardest one to see. But here I've got f of x equals the cube root of x, which looks like this. Now this one's a problem because when I talk about different points, the problem is going to be right there. Because right there, the slope is straight up and down. And if I ask, what is the slope? We have a problem because slope is rise over run, right? This is going up a whole bunch. You can even pick 2 points, 1, 2 points on that tangent line. So slope goes up, let's say it goes up 2, but it doesn't go over any. That's 2 over 0. That's undefined. Vertical lines have an undefined slope, which means if I say, what's the derivative? You'd have to say, well, the derivative is undefined, which means it's not, right? You can't find a value. You don't have a value, you don't have a derivative. So it's not differentiable there. I've got another explanation for the same thing I just said right here. At x equals 0, the slopes are approaching infinity, right? That's going closer and closer to a vertical line. The tangent line becomes vertical here, and the slope of vertical line is undefined. I guess it's the same argument I just had. Basically saying vertical lines don't have a defined slope, so you can't have a defined derivative there. So there's our third problem. Functions are not differentiable at a vertical tangent. The last one we had mentioned earlier is probably easiest to spot, a little harder to prove why. But it's when you have a discontinuity, some kind of jump discontinuity or infinite discontinuity or any kind of discontinuity, really. If you got a discontinuity, there's going to be a problem with figuring out the slope because you're saying, well, here, even just, yeah, there's a problem with figuring out the slope because you just suddenly jump to a different value, right? What do you get? The slope on this side is not going to really inform me about the slope on that side. So it's pretty easy to spot. You can prove it with our derivative function here, right? This one I actually used the limit definition of the derivative to find the slope at 0. And from the right-hand side, I got a value of 0. But from the left-hand side, I got a value of negative infinity. Those do not agree. And remember, if the limit from the left and the right don't agree, the limit as a whole does not exist. If I ask the limit as h just approaches 0 without putting a left or a right there, I would have to say that this limit does not exist because the values from the left and the right don't agree. So that's the last one. Functions are not differentiable at a discontinuity. So there are 4 of them. You should know. I'm going to get rid of this for now. All right. So recapping, because this part's important. There are 4 points, there are 4 problems with differentiability. 4 problems when I can't find the derivative. And those 4 are corners, which looks like this. Cusps, which look like that. Vertical tangents, which is more when I have a case like that going on. And discontinuity, right? Which there's all sorts of types of discontinuities. There's jump discontinuities. There's infinite discontinuities. There's oscillating discontinuities. And there's even removable discontinuities, right? So we have a problem with any of those. You should definitely memorize this. These 4 are often quizzed on AP exams. They'll they'll certainly show up on your next quiz. Like, memorize that. That's when you have a problem with finding the derivative. Can't find it at corners. Can't find it at cusps. Can't find it at vertical tangents. Can't find it at discontinuities. Write those down. Memorize it. Make sure you know those ones. All right, back to the original problem. Sometimes students kind of freak out because they're like, wait a minute, what if I see that? When do I know if there's a problem or not? And the easiest is just graph it. All right, so here I graph y equals the cube root of 3x, sorry, y equals 2 times the cube root of 3x minus 6. I'm graphing it, and yep, sure enough, looks like there's a vertical tangent right here. That looks at 1, 2, 3, 4, 5. Looks at x equals 2, there's a problem. I could have probably figured that out by looking at this, because if I put a 2 in there, 3 times 2 is 6. 6 minus 6 is 0. That's going to give me the cube root of 0, which exists. It's right there, but I could have probably intuited that that might be where the problem lied. But yeah, so clearly I've got a problem at 2. Everywhere else, it's fine. I can find the slope here. I can find the slope here. I can find the slope here. Sorry, I don't think you can see my mouse. I can find the slope here. I can find the slope here. I can find the slope here. But I can't find the slope right there at 2 because it's going to be a vertical tangent. So, answer to my question, For what values of x is it differentiable? It's differentiable for everything but 2. So my answer is going to be everything from negative infinity all the way to 2, but not including 2 because I've got a problem there. Union everything from 2 to infinity. Just as a recap, we should know this, but remember there's a difference between this and this, right? If you have that bracket, that means including 2. If you have a parentheses, it means not including 2. I did not want to include 2, so I used parentheses on both of those. All right, we should be aware of that, but sometimes people need a reminder, so real quick reminder. All right, next page, we are almost done. There's a couple theorems you should be aware of. This first one's actually probably one of the most important. Differentiability implies continuity. If f has a derivative at x equals a, then f is continuous at a. All that is saying is that if you know you have a derivative at a point, then you absolutely have to be continuous at the point. And we know that's true because if we weren't continuous, right, that was one of our problems for continuity. Like if I have a discontinuity, then let's try it again. We knew that because if I have a discontinuity, then I'm not differentiable, which means if I'm differentiable, I absolutely can't have a discontinuity. Otherwise I wouldn't have been differentiable. So this theorem says that as long as you know you have a derivative, then you know you're continuous. So if I say there's some function that's differentiable everywhere, you would know it's continuous everywhere. You know there's no discontinuities anywhere in there. It's a continuous function. It goes, well, right, there's not a problem with it. It's continuous everywhere because it's differentiable everywhere. The converse is not true. Remember the converse switches the if and the then, so I'll write the converse out really quick. If f is continuous, then it is differentiable. Now that is not necessarily true because I can definitely have a continuous function, but it's not differentiable, or at least not differentiable everywhere. Maybe pause the video, see if you can think of an example. All right, here's some examples. I've got a function there that is clearly continuous, but I've got 3 problems for differentiability. It's not differentiable there. I tried to make that a corner. It's not differentiable there because of the cusp. And it's not differentiable there because I've got a vertical tangent, right? So I can be continuous without it being differentiable, but I can't go the other way around. If it is differentiable, then it absolutely has to be continuous. All right. The very last one is just something we're going to talk about more in the future, but something just to be aware of now. It's called the intermediate value theorem for derivatives. We remember the intermediate value theorem, hopefully. If not, here's a recap of the intermediate value theorem. Intermediate value theorem just said that if I had some point here, like I put an A in and I get some point there out, and I had some point B, and I knew the function was continuous, that meant that if I went from A to B, and it was continuous, no breaks in the graph, I would have to take on all the values between f of a and f of b. That was our intermediate value theorem. For derivatives, it's very, very similar. Same type of idea. For derivatives, it's just saying if you've got some differentiable function, and you know when you put an a in, I get f of a out here, and I put a b in, I get f of a b out there. If it's differentiable, it's definitely also continuous, but that also means there's no cusps or corners or anything else there. So if it's differentiable, it's some nice smooth curve without any of those cusp or corner problems or vertical tangents. And it's just saying, hey, the derivative from here to the derivative there, I'm going to take on every value between those 2 things. I'll try to come up with a good example. Let's actually start here. Let's start with one like this. Sure, like that. So if I look at the derivative at a, I can look at this and say, well, I'm clearly going down, so the derivative is negative, right? If I look at the derivative of b, it's clearly going up, so the derivative is positive. What this theorem says is it says that my value of the derivative will take on every value between this negative number and that negative number. Let's just pretend this has a slope of -1, and let's call that a slope of 3. That means somewhere in that interval from a to b, I'm going to take on every value for a slope between -1 and 3. I'm going to have a slope of 0 somewhere. I'm going to have a slope of 2 somewhere. I'm going to have a slope of 1/2 somewhere. That's the intermediate value theorem. In fact, we could probably look at that. If I said, where are we going to have a slope of 0? You probably could look at right at that bottom, like, yep, that's a slope of 0. If I said, when am I going to have a slope of 2? You might like, well, it's not going to be as steep as this one here at 3, but maybe right about there. Maybe that's a slope of 2, right? So that's all the intermediate value theorem is. It says as long as you know you're differentiable over the whole interval, then the values of your derivative, the values of your slopes, will take on every value between that first number and that second number, that first slope and that second slope. All right, that is it. Your assignment is section 3.2.1, doing those problems there. Again, just making sure you understand probably the biggest part of this lesson was the easiest part. Those 4 times you have problems with differentiability. Corners, cusps, vertical tangents, and discontinuities. Those are problems with differentiability. You can't find the derivative at any of those. As long as you don't have those, you can find the derivative. See you next time.